equation up here, and this would be an equation for a level surface of this function of 3 variables. I'm just going to name that f of x, y, z. And I'm asking us to find an equation for the tangent plane at this point. Now, one huge word of caution here. When you see tangent plane, you might say, oh, we've done that already. We know how to do that. That's the local linear approximation. It is not the local linear approximation of this function, however, because this is a function of 3 variables. Its graph is in 4 space. If I tried to approximate the graph of this function, I would be doing that with a hyperplane in 4 space. That's not what I want. So when we looked at tangent planes before, we were looking at functions of 2 variables, and the surface that we had was the graph of the entire function. Here, this is a different type of surface. I've got a function of 3 variables, and I'm not working with the graph of that function, which would be in 4 space. I'm working with a level surface, which is a subset of the domain. So, I'm still finding a tangent plane. Geometrically, it's the same thing, but algebraically, the technique that I used for finding that formula is going to be different. What I'm going to do is take advantage of what we just learned, which I like to paraphrase as, for differentiable functions, if the gradient isn't 0, the gradient is normal to the level thing. Now I say level thing because if, as I have here, I have a function of 3 variables, I'm going to have a level surface. If I have a function of 2 variables, I'm not going to have a level surface, I'm going to have a level curve, but it will still be the case that the gradient, if not 0, will be normal to that. So the generic version is that for differentiable functions, non-zero gradients are normal to the level thing. But that's cool, because now I'm looking for a plane. I need a normal vector. I can work with that. So I'm going to just use point normal form. So I'm going to need a point, and I'm going to need a normal vector. When we had a function of 2 variables, we didn't use point normal form. With a function of 2 variables, the gradient was a vector in 2 space. So it couldn't be normal to my plane that was going to be in 3 space. I would need a vector in 3 space for that. But we were able to build the plane by saying, hey, the z-value on the plane should be my starting z-value plus some change. So we were able to use the gradient in determining that amount of change, but we weren't able to use it directly as the normal vector because it wasn't even in the right space. Okay, so let's see, the point, oh, that's easy, that was given. And I will point out, I did in fact choose a point that is on this level surface. If you plug in this point, it does make the equation true. All right, excellent. So now my normal vector, I'm going to call it n, but that's going to just be the gradient of f at 1/2, 0, 2. And as always, finding that will be a two-step process. I've got to first of all find the gradient function and then evaluate it at that point. So the gradient of f, I know that's just f sub x, f sub y, f sub z. That's going to be partial with respect to x is just z. Partial with respect to y, the y only shows up there, so that's going to be z e to the yz. Partial with respect to z, I get an x here and a y e to the yz here. So x plus y e to the yz. Excellent. So then the gradient of f at 1/2, 0, 2 is going to be 2. 2 times e to the 0 is also 2. Let's see, x was 1/2 plus 0. So we get 2, 2, 1/2. Excellent. Okay. So I'm just going to call this point here P. I'm going to let Q represent an arbitrary point, x, y, z, that's going to be on my tangent plane. And then I'm going to say, if I were to form the vector PQ, that would just be x minus 1/2, y minus 0, or y, z minus 2. But what I know is that n dotted with PQ has to equal 0. Because if this is normal to the plane, that's going to mean it's going to be orthogonal to any vector that's parallel to the plane. And if PQ is connecting points on the plane, it's parallel to that plane. Okay, so we've got 2, 2, 1/2, dotted with x minus a half, y, z minus 2 will equal 0. 2 times x minus a half plus 2y plus 1/2 z minus 2 is equal to 0. If you want to simplify further, you can. I'm fine once you've gotten to the point where you've got an equation with just numbers and variables, you've gotten rid of the vectors by actually evaluating that dot product.